Okay.
Yeah, hello everyone. Welcome to today's ASAP seminar. Today that we are happy to have Kaiyue to talk about fantastic pre-training optimizers and where to find them. Kaiyue is a second year PhD student at Stanford University, working with Professor Teng Yuma and Percy Liang. He is a Tsinghua University alumnus from the Yao's pilot class. His research spans theoretical and empirical deep learning with a long-term ambitions to uncover the physics behind deep learning. Recently, his work mainly focuses on demystifying algorithms choice in the pre-training. Today, he will talk about the difference between different pre-training optimizers and how we can design a good one. Yeah.
Sounds good. Thanks for the introduction and thank you for having me. Yeah. So I will just get started. Uh, okay. I guess this is the first time I'm giving a talk about this paper, so like there could be like some confusion, and then if anyone has any questions, please feel free to just interrupt and then ask. Uh, so today's topic is about pre-training optimizers. Uh, and like there is a questions that has been like very close to my heart for quite a while now, which is like why AdamW has dominates like all the large scale training for so long until although like there are like many claims of like high speed up from like alternative optimizers that claims to have like for example 2x speed up from AdamW, like if waste of like algorithm design if like the speed up is real and people are not using them. And so we conduct this like benchmarking to try to figure out like what's the issue, and through like a fair tuning and across like many different model scales and then different chinchilla ratio, we discovered the following two facts, like the two observations. Like the first one is that like all the AdamW variants that can be classified as a scalar-based optimizers, which means they operate on scalar level. They didn't reach like large speed up as claimed. Instead, like they roughly have only 10% speed up over like AdamW. And for the optimizers like Muon and SOAP, which are like fundamentally different in terms that they are operating on a matrix level, they can reach very high speed up, like roughly 40% speed up over AdamW on small models. By small, we mean like models smaller than 0.5 billion. But like the speed up seems to decrease with scale. And the issue is like the reason behind this is like still open, and we think it's an important open problem to study. I will offer some of my thoughts at the end of the talk, but I don't think anyone actually knows the exact reason for now. And so to give a background for people who are not very familiar with optimizers, like AdamW has been the default optimizer for, I think for nowadays, like until Mion, it is the default for like almost all the deep learning models. It operates on a scalar level, which means that like it will update every scalar in the neural network weight in parallel using the historical gradient. So like there are like essentially two momentum that the AdamW need to store. The first one is the first order momentum MT, and the other one is VT, which is a second order momentum, and it's essentially a exponential moving average of the square of the gradient. And then the final uh update will roughly be MT over square root of VT. So like one can imagine Adam as a smooth version of like sine gradient descent. So if ignoring all the momentum, then this will be the update will just be the sine of the gradient. Despite the large empirical success of AdamW, so like I think the Adam paper is also received like a record like numerous award like over the years. It is actually not very ideal theoretically in terms that like actually under some of the hyperparameters Adam doesn't even converge, and even in the setting that it converge, it doesn't reaches the highest theoretical convergence rate in the convex setting. So like people from the optimization community has tried like multiple different tricks to in the original convex optimization literature to try to further speed up add-on. So like one of the important trick that people tried is called Nestor of momentum. So compared to add-on W, Nestor of add-on W is also very simple. The only difference is that instead of taking the original momentum, like on every step, the algorithm will mix the momentum MT with GT again. So like the actual like momentum used to compute update will like lean more heavily on the current step gradient uh compared to add-on W. So like this may look kind of weird if you are not familiar with like convex optimization literature, but one can prove that like this will have a high if you don't consider add-on W but instead consider SGD, then Nestor of SGD can have like higher convergence rate compared to the plain version of GD. And the reason behind this is roughly that the update has like less variance across time. And so like the update is roughly speaking more consistent. There are definitely like many other optimizers that share the same high level intuition, but end up with like very different algorithm choices. Like what is GT? Oh, sorry. Like GT is the gradient of WT at step T. So like you take WT and then you compute some version of loss, for example, the next token prediction loss, and then you compute the gradient. And the GT means the gradient at that particular step. So in this case, it's just a scalar. Sure, sounds good. Um, yeah, uh, uh so basically like people has tried like many different algorithmic improvement which shares this roughly the same intuition that Adam may have some form of oscillation in its update, and then people want to reduce the variance of the update using some of the method like some and then we will also consider some of them later. uh but for example, like Mars, like the algorithm that is proposed last year, also on the topic of pretraining, shares the same intuition that it want to reduce variance for add-on, and then it can also be used to reduce variance for other base optimizers as well, but we will not touch that in this particular talk. So, but all of these are like in spirit very similar to the original version of Aden in terms that they are all operating on the scalar level, meaning that like all the momentum and update are computed parallelly for every scalar, and then in terms of computing the optimizer update, you don't need to consider any interaction between different scalar weight. A much more aggressive approach is to change the subject of optimization completely and then actually operate on the matrix level. So like for neural network, most of the operation are actually just matrix matrix vector product where the weight is the matrix and the hidden vector is the and it times the hidden vector to get the next output. So it kind of makes intuitive sense that we should actually consider the weight matrices instead of like just plain scalar. And one of the first paper to study this is Shampoo, which they actually consider the object WT as a matrix. And here GT means the gradient of WT, which is also a matrix with the same shape in this particular setting. And like what Shampoo do is essentially it maintains like two momentum, which are actually the outer product of the matrix GT, and then in the final output it computes like the negative 0.25 power of LT and RT and then times it on both sides of GT. There's a quite fundamental theoretical reason to do this, and the reason is that this is well, the Kronecker product of like the Adagrad, but but actually like later it turns out that the theoretical motivation is not that important. For example, like 1/4 can be changes to like some other power as well. Like some people propose to use 1/2, and some other people propose to use 0.2. So like it's not that critical of like the actual form is not that critical. But like one of the things that people empirically know is that at least the algorithm that I'm presenting here, the vanilla shampoo, is not a very stable optimizer. It actually requires a lot of careful tuning, and also the operation like -1/4 requires a very high precision calculation. So like in the recommended implementation by Google, uh, the the power is actually computed in FP64, which is like actually not supported on some of the hardware even. So it's very hard to get shampoo to work. But the very recent successor, Muon, actually like solved this issue almost completely by introducing a very numerically stable process to compute an update that is conceptually similar to shampoo. Uh, the Muon algorithm like looks essentially like this. So there is a momentum, the first order momentum of GT, which is something that is roughly the same as the momentum uh in Adam, because like the addition can be viewed as in scalar level as well. And there is another operation which is the Nestor of momentum step, which you again like strengthen the weight of like the current step GT by mixing it with MT. Uh, and finally, like people just do do an orthogonalization of like this particular momentum, and the orthogonalization here actually means some operation that is shown in the that is essentially approximating the operation in equation one. So this means that roughly speaking, you want to find an update that has a small operator norm, and which is in this case like constrained to be one, and while the update should have like the highest dot product with the gradient and or the momentum. In this case, we are like kind of using them interchangeably conceptually, although like practically they are like slightly different. Uh, and the way that this particular operation is implemented is through the composition of like of the following polynomial. And by choosing ABC very carefully, we can get like a decent approximation of the orthogonalization here, and empirically muon can be like can show like speed up over Adam in this way. Uh, but going back to the like to the motivation of this particular paper, well, like there seems to be like quite a lot of optimizers. Like in the very brief introduction, and I have already introduced this perhaps like 3 to 4 optimizers other than Adam. It's very unclear on like what's their performance. And actually, different papers are contradicting each other on this particular topic. So for example, these two figures are both taken from like some other papers that is introduced this year. Like the first figure is from the Mars paper, which is the in this plot the red curves, and it shows that like Mars seems to have a very high speed up over Adam W. However, Muon in this particular baseline, in this particular comparison, seems to be actually slightly worse than Adam. And and but in a like in a almost like in a paper that is almost published in the same time, it is shown that Muon seems to have like a 2 times speed up over Adam W. Uh, where the settings and the at least the model scale seems to be like roughly the same, because the in the right plot the figures are also plotted in a regime that is roughly 1 billion parameters. Uh, and the reason behind this seemingly contradiction is that in almost all the cases, optimizers are not evaluated in a respectively best practices. So, for instance, in the left figure for Mars, the muon optimizers are actually like used over for all the weight matrices in the transformer, where the best performance of muon can only be released can only be shown if you actually use Adam W for all the for example the layer norm weight and embedding. So so like this like kind of arbitrariness in terms of baselining can give us like very different result when we are comparing different algorithms, and make it very confusing for people who are not very familiar with optimizers on like how do we compare like all of this different algorithmic change and what is working and what is not. And to make things even worse, among like many of the literatures, even the very classical baseline N and W are not like fully tuned. For example, from works that is starting from Sophia, and some of the paper including cautious Eden, like which are all essentially claiming a roughly 2 times speed up over Eden W. They are using a for the baseline. They are typically using a learning rate that is inherited from the GPT-3 recipe. So in that particular recipe, OpenAI recommend to use a 6e negative 4 learning rate for 100 million models. While this learning rate can guarantee very stable training, it is actually very far from the optimal. So in the right figure, we are showing a simple ablation where we keep everything constant, every other hyperparameter constant, but only increase the learning rate from 6e negative 4 to negative 3, which is the red line in the plot. And comparing the brown line and red line, you will see that by just increasing the learning rate by a factor of roughly 10, we can see a more than 2x speed up, uh, comparing like a well-tuned add-on versus add-on. And if you put some of the add-on variant in the same plot, you will see that actually in this particular setting, they no longer provides like the speed up provides a large speed up over add W. Instead, some of the optimizers shown here are actually slightly worse than the tuned add W. And also, it's worth noticing that like we for Mars and Nestor of add W in this plot, they are also using a relatively high learning rate. And so like this means that once that everything is tuned, the order may flipped. The order between optimizers may like flip very compared to the original claim in the paper. And another practice that people usually do when comparing optimizer is that people try to fix the shared hyperparameters across optimizers because like it feels very hard to tune all the hyperparameters. And for simplicity, people just say that okay, we will for example set weight decay to be a standard value, fat value, which is 0.1, and then we may also set, for example, beta 1 and beta 2 to be some standard value like 0.9. And this on the surface feels like a very fair comparison because like the hyperparameter roughly have the same meaning, and especially in the case that the optimizer are also roughly conceptually the same with only a small changes. You People may feel that like the it is it is fine to set all the hyperparameters constant, and then like just compare the two algorithms, uh, given that they are like conceptually similar. However, we actually can show that this is not the case, even for like two very similar optimizer like Adam and Lion, where as mentioned, as mentioned, they are actually roughly the same. If you ignore the momentum term, if you ignore the second momentum term in N W, and they will, and however, it is actually the case that if we sweep the learning rate, if we sweep the weight decay very properly, we can see that the difference between Lion and N W can be significantly shrinked if we use a much higher weight decay for Lion compared to N W. And this is actually something that people wouldn't take notice in the old methodology where we keep all the hyperparameter constant, but only compare the algorithmic part. So it is actually there is no shortcut where when it comes to comparing optimizers, because there are a lot of nuances and subtleties regarding like how to choose hyperparameters, and a hyperparameter chosen like improperly can actually flip the optimizer ranking kind of arbitrarily and lead to like many different noisy conclusion. So our proposal is that if we don't know like the theoretical reasoning or like the principled way of like, or if we don't know the easy way of like comparing optimizers, or at least not there, if we cannot find an easy but trustworthy way, then let's just do everything in a very dumb way. So like as I mentioned, like people may think that sweeping every hyperparameters is like first too time consuming and very hard to do. But in this paper, we almost do exactly the thing that I was trying to mention. That we sweep like for many optimizer like every hyperparameters in some small region, and based on the result on the small compute region, we identify some of the sensitive hyperparameters that really requires very careful tuning, and then we sweep them like extensively over more regions to try to get a better to try to get a thorough picture across the compare for the comparison of optimizers across this region. And finally, to extend out to check our result on like even larger model, because we couldn't afford to actually do the same amount of fine-grained sweeping on 1.2b. We used some of the standard practice like scaling laws to extrapolate to like a large model. In our case, it's not that large, but it's still larger than the previous experiment. We then extrapolate to 1.2b and from 1x to 8x chinchilla for some of the chosen optimizers to further compare their performance. So roughly speaking, in our study, we try to follow the following principles. We want to tune every hyper optimizers roughly separately, so that and each one should be compared towards the end of the training. And finally, like we want to evaluate across as many model scales and data to model ratios as possible, because we kind of suspect that the ranking of optimizers can change when it comes to different model scales and different chinchilla regime. And that's actually also true, and we will show this later. So to go into the details of our experimental setup, we there are four model sizes that we consider, and the architecture are roughly following the Llama architecture. And for the data, we for each model size we consider 1 to 8x chinchilla optimal tokens. And for those people, for those who are not very familiar with chinchilla, it just roughly means 20 times the parameters account of tokens, and is believed to be roughly how you should like how you should like uh assign your model size and token size when you have a fixed amount of compute. But in practice, people typically train for like much more than 1x chinchilla. So we experiment the effect of like overtraining to 8x chinchilla in our paper. And for the optimizers, we tried 11 of them, and most of them uh, except for the muon, soap, chrome, and cyan. Like the others are all scalar level, and the muon, soap, chrome, and cyan are like matrix level optimizers. And for our most like the metric that we care most is the end of at the end of the training, what's the C4 losses. So like there are some paper by AI2 that shows that this particular C4 loss has a very high correlation with the downstream performance. So we choose this as like our primary object. And but just to verify like whether the optimization benefit is transferred to downstream task, we also like test some of the downstream performance on benchmark like Halesweg, ArcEasy, and BooQ. And and all of our runs and the results are shown in the paper, and we essentially open source everything from for almost every run that we run. And so if you are interested in the some of the details, you feel free to check out our paper. And for our phase one, we run the per hyperparameter sweeping on the 0.1b model for all the chinchilla ratio, and for 0.3 billion model and 0.5 billion model in the 1x chinchilla ratio. And for our phase two, we uh, we perform the sweeping on scale sensitive parameters on 2 to 8x chinchilla ratio. And finally, we extrapolate to 1.2b as mentioned. I see there's a question. Have you ever differentiate muon optimizers in the original and do you mean the one by Moonlight? Oh, so essentially we didn't include the result in the paper. So we are using the one that is the muon optimizer that we are mentioning here are the one that is used in NanoGPT speedrun. I believe like the one that you mentioned that is which is introduced in Moonlight, has essentially two different from the Keller Jordan's version. The first one is that they use a different per module learning rate scaling, and the other one is that they introduce decoupled weight decay. So for our version, we also have decoupled weight decay, but we don't have the same per module learning rate scaling as the Moonlight version. We have it for the Keller Jordan's version, and the reason behind this is that uh, like the Keller Jordan in the NanoGPT speedrun, they actually transition from the version used in Moonlight to the version that we are using, and also the speedrun is currently using. And the version that we are using is like roughly more mu-p consistent. And if we are like doing the initialization according to mu-p, you should expect the version that we are currently using should have like a constant learning rate transfer. And for the one that Moonlight is using, you need to scale down your learning rate by 1 over the width. But in any cases, we essentially strip the learning rate for like separately for the weight and for the embedding. So I think there is like essentially roughly speaking, like the effect should be the difference should be small. But I also run some of the comparison like I've also run some of the comparison, and I don't see like at least on the smallest scale, I don't see there is a large difference. But yeah, whether this will cause a very different result when scaling up, I'm still not certain. Yeah, do we have any other questions? Okay, if not, I will just continue. Oh, sounds good. Thank you. Uh, Yeah. So to illustrate how we do the coordinate descent, for how we do the sweeping for the first hyperparam for the in the first phase, essentially we will choose an initialization hyperparameter config, and then for every axis, for example, in here we are showing like axis is like learning rate, weight decay, and mean learning rate. We will do a grid search fixing all the other hyperparameters, and then we will choose the round that reaches the lowest loss in the grid search. For example, in the round one, we find out that if we increase the amount of warm up, the loss can decrease by roughly 0.02. And then we will just use this as our new initialization, and then perform a grid search over all the coordinates again. And for example, here we show that like the batch size can be reduced, and the max gradient norm can also be should also be like slightly larger than one. And in our convergence criteria is that when the loss is decreased by no more than 3 inactive 3, then we will stop the coordinate descent, and then choose the best performance one as the hyperparameters for this particular region. And so essentially, when the run is finished, we should be able to see a table like this, which are all presented on our paper. That for the hyperparameter we choose, what will the effect be if we like turn just one of the coordinates in the hyperparameters, and the one that we choose should roughly be approximately the best hyperparameter in the Pareto sense, that if you change one coordinate, like the performance should monotonically increase. Sorry, the loss should monotonically increase. So like this should be the best performance one if you don't consider joint scaling like two hyperparameters. Uh, Ideally, people should also like consider perhaps joint scaling, but the reason why we didn't do this is still roughly due to compute constraint. But if we believe in some of the basic assumption about like the theory on how hyperparameters should scale, I think there is very hard to find a counterexample that if we choose the one-dimensional grid search to be fine-grained enough, uh, then roughly speaking, this should converge to a first order minimum in the hyperparameter space. And uh, and continuing that, we for the results in the first phase, we for every optimizer and regime in this phase, we identify a coordinate-wise local optimum over all the hyperparameters, and then we have two observations based on the result. The first one is that loss is actually sensitive only to a subset of hyperparameters. So most of the hyperparameters actually have a very little effect when perturbed, like near optimum. And further, among the sensitive ones, like many has a constant values in the model scales that we and data to model ratio we study. So it's roughly safe to choose them to be a constant for for extrapolation. And and then to save some of the compute, we then only do a narrower sweep constraint to this to the subset that are both sensitive and then also changes with scale. And to provide a rough picture on like what are these hyperparameters, we show the scale sensitive hyperparameters for the four optimizers here. So essentially, like for mu, it is very stable, and only the learning rate of mu is a scale sensitive hyperparameters. And but for Adam, like a lot of hyperparameter can affect the performance by a lot. For example, it's very critical to set the batch size correct for Adam. But for mu, like the changing the batch size, for example, for 2x has like a small effect on the actual performance. And and after we finish the second phase sweeping, we end up with like a rules portfolio for all the optimizers we study in the for model sizes smaller than 0.5b. And the result looks the result roughly looks like this. That if you like the all the dashed line in the right in the left plot are actually scalar level optimizers, and all the solid line are matrix level optimizers. So it's very apparent that there is a difference between scalar level optimizers and matrix level optimizers from the loss perspective. That the matrix level optimizer is roughly like optimal across different data to model ratio compared to the scalar level ones. And also, these changes in the loss is significant enough to be reflected on the downstream performance. So, for example, look at the Halsweg performance for mu. It is roughly 1% better than Adam, actually 2% better than Adam. Although their losses may look although still roughly close, but it's the difference is only roughly about 0.02, but the it can be reflected in downstream task already. And looking at the how the speed up, so to measure speed up, we actually consider the effective data size an optimizer need to run to get the same loss as Adam. So like uh, a speed up of 1.2 means that the optimizer only need to run roughly 80% of the tokens to get to be trained on 80% of the tokens to reach the same loss as Adam. And uh, and so looking at the plot, we can see that the all the matrix level optimizers are like very performant. And compared to Adam, they can reach a roughly 1.3x to 1.4x speed up. And the speed up is like noticeably higher on the smallest model. But once the model size increases, in this phase, it drops from 1.4x in the 100 million models to roughly 1.3x in the 300 and 500 million models. And all the scalar variants are actually roughly within 1.1x of Adam W, except for the smallest model size. So like for 100 million models, they can roughly reach a speed up of 1.2, but for slightly larger model, the speed up dropped to like 1.1. And uh, there are two special optimizers here, which are actually not designed for speeding up, but designed for saving memory. Like the which are the one which are like Adam Mini and Lion. And there is actually an interesting trend about these two optimizers as well. So if you look at the green dashed line, which is Lion, on the smallest scale, it's actually a better optimizer compared to Adam, reaching a roughly 1.2x speed up. But once the model size scale, the speed up effect of Lion quickly diminish and actually is overtaken by Adam W when the model size increased to 0.5b. Uh, but the story is very different for Adam Mini. So for Adam Mini, it's like worse than Adam on the smallest two models. But once the model size increases to large enough, it actually can overtake Adam and has and essentially have very similar performance for larger models. And in our final phase, we do a hyperparameter scaling law for the hyperparameters we found in the first two phase. And the input of the scaling law are the data amount and the model sizes. And then we fit a roughly a power law for every scaling sensitive hyperparameters and on the observed triples per optimizers. And we extrapolate this by just putting in numbers like 1.2b model and 1x chinchilla. And to validate the hyperparameter scaling laws are giving us a roughly correct hyperparameters. We do the same hyperparameter sweeping for Adam W on 1.2b model and 1x chinchilla, and we validate that the predicted hyperparameter are actually within 3 - 3 final loss of the full sweep optimum. It may not be the optimum of like all the possible hyperparameters because it's definitely like there's no way to tell. But at least comparing to our like more thorough methodology in phase one, like the extrapolation quality is like not that terrible. Like it's still roughly having the same performance as even if we didn't strip the hyperparameter on the 1.2b models. Uh, for like which is something a counterfactual statement because for Adam W we actually did, but for the other optimizers we didn't strip all the hyperparameters. And we do two kinds of like extrapolation study. The first one is that we study larger models, which is a 1.2b models, and the other study is that we study a more overtrained region where we study like 16x chinchilla uh, on the smaller models. And the result of the model scaling is particularly pessimistic, and it's actually, to be honest, is unexpected from us because we actually observe a very high speed up of mu and compared to Adam W on the smaller model. Although it's decreasing, but it's only decreasing from 140% to 30%, which is still very high speed up. But on the larger model, we see that both SOAP and mu are actually like losing their speed up in the ATX chinchilla region. And even before that, one can notice that the speed up is only roughly 10%, and uh, but the which is like significantly lower than the 30% in the smaller models. But I think there is definitely like some possibility that the hyperparameter chosen here is like not as the one that we sweep for in the smaller models. So to try to address that, I sweep the scale sensitive hyperparameters for mu on the 1.2b model as well. So but effect is the final result is roughly the same. That like the speed up is still decreasing when the model size and data size jointly increase. And so we reach the conclusion that both mu and SOAP can only have like roughly 10% speed up on the 1.2b ATX chinchilla region, which is the largest scale experiment we run. But if you put it in the global picture, it's definitely not a large model. It kind of suggests that the speed up of this matrix level optimizer are decreasing very fast. But but still the good news is that all the optimizers are still having some speed up over Adam W, and especially the simple variant Nestor of Adam, it still has a 10% speed up. And on the result of data scaling, we also observed another shortcoming of mu, but this one may not be that significant. But in all the model sizes that we study, mu is like it will always be outperformed by SOAP once it is like roughly overtrained in 8x chinchilla region, except for the 300 million model. So for the 300 million model, we run the experiment on the 16x chinchilla, and we then observe that actually SOAP is overtaking mu. Although you can see that from the plot that the difference is definitely not large, but still the order will flip when the chinchilla ratio increases. So we have a conjecture that because mu is roughly only keeping a first order momentum and not keeping any version of is there any results of scalar based? Oh yeah, yes there is. Uh, so so like the nestor of Adam W, which is the purple line here, is actually a scalar level optimizers. And as you can see, like it is still having some speed up over like Adam W, and on the ATX chinchilla regime, it roughly has a 10% speed up. Uh, Yeah, so going back to the data scaling part, we suspect that the second order momentum kept by soap, which is roughly the second order, is roughly the same as the second order momentum kept by shampoo, can have a higher can be more effective when the data to model ratio increases, and perhaps when you run for longer, the adaptivity to the difference in the parameter direction in the different sharpness in the parameter directions can lead to a slightly larger speed up compared to the mu, which is the steepest descent algorithm, and then conceptually move in the equal spaces for all the direction. But we believe that whether like this is true or like whether the effect of soap versus muon can be validated on larger scale is also an interesting open problem to study. Uh, and to show that, to further strengthen the fact that like hyperparameter tuning is actually pretty crucial, we can show that the difference between two optimizers are really subtle by picking some of the examples. Uh, for example, in the 500 million ATAX chinchilla region, when we just set the learning rate of SOAP to be 2x larger than the optimal learning rate we find, we can see that although there are some small spikes, the run still converge quite successfully towards the end. But and it reaches roughly the same loss as Mars. It is very likely very hard to tell visually, but the loss is slightly higher than Mars. Uh, but once you set the learning rate to be like closer to optimal, then there is a pretty significant gap between Mars and SOAP. So this means that like even a small changes in the learning rate, which is only 2x, can lead to a flip in optimizer ranking. So our recommendation is that we should at least the scale sensitive parameters should definitely be swept in future optimizer study. And and for the other methodology that people may use in some of the study is that people may compare two optimizers before the run finish, and it's kind of a reasonable mistake to make because if the gap is seems very large at some point in the run, then it may feels like the some of the optimizer may never be able to catch up, and it's roughly it's kind of uh almost acceptable to stop some of the run. But in fact, if one look closely of the different loss curve between different optimizers, we can see that the difference in loss can actually shrink quite significantly during the run. For example, comparing Nestor of Adam and Adam here, the difference are like a relatively larger in 20k step, but like it decreases to a very small value at 80k step. Uh, and even to make things even worse, the order between the optimizer can flip like for several times during the run, comparing Mu and Adam, for example. And in this case, if you compare at a different point, say if you compare at like 70k, then you will reach the conclusion that Mu is actually a quite poor optimizers. And the second result is roughly the same conclusion as the one that is shown in Moonlight, that weight decay is really crucial for good performance of Mu. And if the weight decay is set to 0, you will see a very low loss at the beginning once again. And but then it may lose potential at towards the end of the run, and it will actually be overtaken by a run with higher weight decay when the learning rate is decayed to near 0. So the conclusion that is brought here is roughly that people should never compare things before the learning rate is decayed to almost 0. And finally, there are something that is not directly related to comparing optimizers, but does it means that we should have a weight decay schedule? I I think that's actually a good conclusion. Uh, I didn't mention the Adam C paper here, but I think that's but that's actually a very great paper. So it's connected to one of the phenomena that I'm going to talk about now. So I will I will lead to this later. And so essentially, when we look at the gradient norm and the weight norm of the optimizer run that we run, we observe a quite intriguing pattern that the weight norm are actually following roughly the same pattern as the learning rate decay. So during the warm up, or like slightly during the same period as the warm up, the weight norm will increase, and then it will decrease following roughly the same pattern as the learning rate decrease. And respectively, we see an intriguing pattern that the gradient norm, instead of decreasing, are actually increasing. And are actually increasing during the run. Like this is definitely because like if one is familiar with convex optimization literature, one would expect the gradient norm to decrease once the model is like trained for longer, and it's but empirically almost all the optimizers see the gradient norm increasing. Uh, and actually this is studied in a very great concurrent work by Aaron that is called Why Gradient Norm Increased towards the end of the run. And it actually shows that the first two phenomena that we are showing here are actually related. So when the weight norm decreases, because the loss is scale invariant, you can imagine that moving the weight by a same constant will result in a larger difference in the output. So the gradient norm will actually naturally increase just because the fact that the weight norm is decreasing. So so one of the things that people may like intuitively want is that we don't want weight norm to change at all. And there is a way to do that. And the way is essentially just setting the weight decay to having a same schedule as the learning rate decay, uh, but just with a fine transformation. So if you do this, then the weight norm will be much more controlled. And we have some of the experiment in the marine project that if you are interested, we can discuss perhaps offline. And but roughly speaking, I think this does suggest that setting a weight decay schedule can at least like make the run more stable. I'm not particularly sure whether this will have a performance improvement, but this can like have some other benefit, for example, better predictability or like better scalability of hyperparameters. And for the final observation, we plot the training loss with respect to the primary object that we are tracking. So for our training data set, it's actually a mixture of like many different things. There are like DCLM and there are like some coding data. So there is definitely a domain shift from our training loss to the evaluation loss that we are tracking. But we do observe that like actually roughly speaking they are on the same line, and and it's very hard to tell like for one optimizer from another from this plot. So we tend to the conclusion that at least in the one pass training regime, there's no significant difference in optimizers considering the domain generalization uh, from the training domain to a downstream domain. This is in vast contrast to some of the experiment when comparing architectures. So there are some papers showing that like if you compare, for example, a linear architecture with softmax transformer, you will observe like different generalization trend. And even different linear RNs will have like different generalization trend. So it's kind of blessing that which optimizers are did we find was the most resilient to bad hyperparameters? I would say it's mu or cyan. Like the both are like quite resistant, and Eden is kind of robust as well. But like there are some of the other optimizers that are like very subtle. For example, I think Chrome is one of them. Like it's quite subtle, sensitive to some of the hyperparameters. So like in terms of like sensitivity, you can also check out the table on although this does not provide the full picture, but like the number of scale sensitive hyperparameters roughly like indicates like how hard to turn this optimizer is. Yeah, uh and so to conclude, we have like several takeaway from this paper. Like the first claim is that the first observation is that with fair tuning for all the optimizer, the claim 1.4 to 2x speed up actually shrinks to 1.1 to 1.3x. So it's great to see that actually there is still some speed up to be gained from Adam, but like actually the speed up may not be as large as people expect. And matrix precondition optimizers are definitely the best in class, but still their gains decay with size, which is something that people should take serious study into. And the difference in update rule actually matters in a small chinchilla region where we see muon being like much better than soap and chrome. But actually, this diminishes once we train for more data, and we can even see soap and chrome overtaking muon when we run for long enough. And the other thing is that variance reduction technique like Nestor of Eden or Mars are actually providing essentially a free lunch that they provide a small but a consistent 1.1x speed up over Eden W. And but on the other hand, there is no significant difference we observe between the concrete way to perform variance reduction. Do we expect the gains to decay further at even larger scales? Yeah, I tend not to reach that conclusion that abruptly because it's extrapolation. Extrapolating to 1.2b is like something that we want to be very careful about. So I think there could still be like a consistent speed up like variance reduction technique that we observe like roughly constant 1.1x speed up over older model region. And because like Muon and all the other optimizer like has like variance reduction as a subcomponent, I don't think there will be a word that there is no speed up at all, but that's like just my feeling. But I'm not like 100% sure about this statement, and still I don't think there will be a point that there is almost no gain, but the gain can be smaller. Uh, and and final conclusion is that we should definitely compare at the end, where the learning rate is fully decreased, and skills and data ratios can influence the ranking, and this must be taken in account when we are studying optimizer in the future. And finally, I'm going to share something that is not on the paper. Oh, what happens? Oh, I think there's a small bug, but yeah, this is working. So like thanks to some of the helpful discussion on Twitter, we are having some reflections on our study. So our objective in this particular paper is to find the best optimizer fixing the isoflope. So we just target finding the best hyperparameters that reaches the lowest loss in one pass using a fixed amount of data, which includes the batch size. And but in practice, time is a crucial component, and it actually depends when once your hardware is fixed, it actually depends on the MFUs. And in particular, the hyperparameter batch size actually positively correlates with MFU, which is shown in the left figure, where we see that with higher batch size, we can train with like more token per second, meaning that the training run will be faster fixing the data account. And interestingly, we also observed that, which is consistent with some of the previous paper, that with a larger batch size, Muon actually have a increasing gain compared to Adam. And this I think can account for many of the practical speed up that we are observing in like training larger models like K2, that when people choose when people tend to choose Muon compared to Adam. So for example, in the GOM, the model also uses Muon, and I think in some of the issue they proposed, thanks to the point of Jingyuan, that they also observed the speed up is only 20% on the 4B model they train, but they continue using Muon because they figure out that this can allow them to use a larger critical batch size, which can like allows for larger MFU even if like there is no gain if you only fix the isoflope or fix the amount of data, but allow yourself to choose a smaller batch size. So I think this is another lesson taken. It is actually not contained in the paper, but more like a consequence of the paper, that the real world scenario is more complex than the abstract version, and there are some factors like MFUs and the critical batch size that may not matter that much in academia world where we are roughly compute constrained, but matters much more in the real world setting. Is the wartime? Yes, it is definitely sensitive to a hardware setup. So like is essentially to give a rough picture, like with less hardware you will prefer smaller batch size, and with a more hardware you will prefer larger batch size to fully utilize your hardware. So that's why I'm saying that this is actually like related to to the academia versus industry scenario, because in industry you will in the industrial setting you will prefer a much larger batch size, and it's definitely possible due to the fact that Muon can allow larger critical batch size. It can have even higher speed up than what we report in our paper, because because of the choice of the batch size. So this is the end of my talk, and I think Xingyu is gone. So I'm self-hosting myself at this point, and I welcome all the problems, all the questions that people have. Yeah. So you can send in the chat, or you can just open your mic.
I will just ask the question. Thanks for the great presentation and talking. It's a lot of gains from the talk. So I have two questions. The first one is, you already mentioned that with proper initialization, the mu is kind of extension of mu p, but isn't reason like you did not sweep the initialized seed, because you reported several model sites, but you didn't mention how you choose the initialized seed.
I didn't actually choose the initialization scale. Like I just used some of the initialization scale. I just use a fixed initialization scale that is similar to μp. And it's the one that we use in Marine as a default. So I think there is actually no great reason why I didn't tune the initialization scale as well. But the rough reasoning is that if you can tune learning rate and weight decay jointly, then you can actually simulate like running with different initialization scale. So, and because in our setting we do tune learning rate and weight decay, so I kind of believe that this can at least mitigate some of the effect of not tuning the initialization. Yeah.
Okay, thanks. I got another question. Uh, this this one group of special experiments, you use a smallest model, but you train it with one time chinchilla optimal and up to 8. So basically the training token is increased. Like you got more, the horizon are increased. And from previously paper, uh, if your training tokens are changed, the optimal batch size and the learning rate that jointly change. But from
Yeah, we tune them both as well. Like at least for Adam, we tune them both. Like for different batch size, for different training duration. Yeah. And we do observe the same effect that like with larger model, like with longer training duration, we would prefer smaller learning rate, and in some cases larger batch size.
okay, thanks.
But we don't have the qualitative prediction as other papers. We just kind of like choosing thing adaptively. So what we do is essentially we 2x our training duration, and then we inherent the previous learning rate and batch size we find, and then we try to either lower it or either lower the learning rate or 2x the batch size and see if the performance improve. And if none of them leads to a performance improve, we just tend to the fact that this is roughly the optimal setting.
It's a really nice talk. I have a question. First, mainly for the last experiments about the batch size, have you trained the hyperparameter according to different batch size in the last experiment?
I only tune the learning rate, and not the other hyperparameters in the two plots shown, in the plot shown here. So I do tune the learning rate according to the batch size. So
But you mentioned that the atom is more sensitive to other hyperparameters.
yes, that's definitely true. So like I think there's a possibility that, like, for example, if I tune the warm up uh of Adam, or the weight decay of Adam, I can get a slightly better scaling trend. Uh this is just a primary experiment for the moment, and but I think there is definitely like the gap is too large compared to any gap that we observe. Like a 0.8 gap is like just like too large for any hyperparameter tuning to save, in my opinion.
I see.
But
Uh,
yeah,
do you have an sense of like intuition? What this gap come from? Like
I think there's a
scalar
pretty excellent blog by Leloy Kun on Twitter about like why muon may prefer larger batch size. And the intuition here is that muon like roughly move in the same scale in every direction, so it will prefer a smoother landscape compared to Adam. And because the landscape is smoother, you may expect like higher consistency between the update across steps. But of course, I think the problem, academically speaking, is still open, and all of these are just like conjectures. Another conjecture is that when you have larger batch size, like some of the signal may be like some of the low frequency signal may be ignored by Adam, but muon with also organization can amplify those signal and then like can be used to like can try to amplify some of the rare signals so the model can learn better. And I think both hypotheses make some sense, but it's very hard to tell which is the driving factor, at least for the moment.
Okay, thanks. Another question is about the MFU things. Like in the left figure, there's basically no improvements for when the batch size increases after 2 to the power of 20 for Adam.
Yes. For muon, actually.
This is because
this is because I'm using a small small cluster. So like this is only 64 TPU. So like once the batch size is larger than 2 to the 20, then it's compute dominated. So like you don't see a higher MFU.
Sorry, could you say again? Like
so because the cluster that I'm using here is not very large,
yes.
So when the batch size becomes too large, the compute is the dominating factor. And you couldn't get free MFU by just increasing your batch size when the compute is dominating, and like you just have to compute all the forward and backward paths, and so like there is no more increasing MFU once at some point.
When the cluster becomes larger, the
turning point will become later.
Okay.
It's also roughly linear. Like the turning point should be roughly linear with the amount of compute you have. Yeah.
So it's mainly it's mainly a compute bounded, like the boundary of compute issue, something like that. I mean, like if the okay, cool.
So if you imagine you are training a large model with comparing to your compute status, then the batch size you choose will be relatively smaller, I think. So it's very hard to tell at the moment, but I think that's the rough picture. That with more compute to model ratio, you will larger batch size. Yeah.
I see. And in that case, the Adam is like I see. Thank you.
In that case, muon will have a larger speed up. Like if you have a lot more compute compared to the amount of the model size you have, you will prefer muon over Adam more. Yeah.
I'm actually I'm actually referring to the gap between like the gap in MFU between muon and
I see. I see.
yeah, there's yeah.
I'm not 100% sure why the gap widens. If that's the question, I think I need to look into that. Yeah, it could be
that definitely be like hardware setup specific formula.
It's possible. Like the gap may be hardware sensitive and also be sharding sensitive to some degree. Like how do I shard the muon optimizer may be
like
influential.
Cool.
Yeah. And so there's a question in the chat about like, do I have any recommendation tags? I recommend Nesterov Aden, Nesterov Momentum, as I kind of referred to multiple times. But there is no more gain that you can get with that particular technique, because muon is already using that. So like there's no more variance to be reduced. I think we do observe Mars having a small improvement over Nesterov Aden in some of the cases. So there's a possibility that like Mars plus muon can be better than the current version of muon, but I don't know whether the speed up can be as large as 10%. Yeah. Yeah. So we are roughly spending more than 1 hour. So is there any other questions? If no, then yeah, I will like call it a day, and thanks everyone for coming. Yeah, and so that's the end of the talk.